Okay. I asked you to show whether this thing is constant, okay? Well, you want the second partial y with respect to x, so let's find that. Then we'll find this, then we'll put it together, okay? So the partial of y with respect to x is second partial of y with respect to x. And of course, what I did there is some people aren't listening today. Haven't been able to check my email, see why that might be. But we just take the derivative of this thing, treating x as a variable and everything else is a constant. So we use the chain rule, derivative cosine of 6x plus whatever is 6 times the negative sign of that same thing. So that should be pretty clear. So I'm not going to do that step every time I get to it. But I'm going to get another factor of 6 here, and the sign is going to, derivative of the sign is going to be a cosine, right? So by the chain rule, I'm going to get negative 144 cosine of 6x minus 13. Then second partial y with respect to t, we use exactly the same idea. If we take the partial of this with respect to t, we get negative t times the negative cosine or the negative sign of all this. Okay, and that negative 3 is multiplied by 4, giving us a negative 12 times a negative cosine, which is 12 times the cosine. And then another negative 3, and we get back to the sine function, and we get 36 there. Okay, so we get this. Do we agree? Yes. Okay, somebody's pointing at something. So let's make sure I haven't done anything ignorant or that nobody has answers. Okay. So there's a difference between two answers. One had 108, another had 180. Okay. Now I was about to get 180 or negative 108, but I left a negative sign out of this. Because when I take the first derivative, I get a negative and negative. That made it a positive sign. But then the derivative of the sign is the cosine, but I get another negative, which makes this a negative 36. So if you just do it carefully, step by step, be careful about your negative signs like I was. It did too much in my paper. Okay, so just adding these, you get that. It's not constant, but it is a constant multiple of the function itself, right? That's with respect to. Oh, y of t here, just to be sure we're thinking this function. And it's not y of t. It's a constant multiplied by your y of xt function. And that might be significant, and it might not. Now, this is related to the wave equation, also the diffusion equation, which we'll talk about a little bit if we have a chance. That's really a differential equations topic, but it involves partial derivatives. And would be something you hadn't seen in a differential equations course. Probably not. Might have, because I think I Jason does do some partial differential equations there. So maybe you did. You know, here is a picture that's really pretty fundamental, and it goes right back to what we've done with these blocks. Okay. So I'm going to make the picture a little bit simpler. So I have some function z equals f of x, y. You know what I just did? I think I had, no, I didn't. Okay, never mind. Z equals f of x, y. Okay. Near some point, x naught, y naught, f of x naught, y naught. And what I mean by that, I mean at x equals x naught equals 0, because you got to specify two parameters for a line. Okay, and here's the point. Y equals y naught, c equals 0. So this point is x naught, y naught, 0. Is that clear? Now we have some function value, f of x naught, y naught. So I'm going to say that f of x naught, y naught is this distance. Okay. And I can project that. Well, if I project, not really project, if I go on the line segment from x naught, y naught, 0 back to the origin, then draw a line parallel to this line back to the z-axis at a perpendicular. So implicitly, this is at a perpendicular. Then at this point, z equals f of x naught, y naught. Okay, that makes sense? Because if I just project this back to the z-axis, the line is going to be parallel to this, because this line projects x naught, y naught, 0 back to the z-axis. That means it goes from this point to the z-axis at a perpendicular with the z-axis. Since it's in the xy plane, it is perpendicular to the z-axis. Then if this one's parallel to that, it's also going to be a projection, and the projection is going to give you the z coordinate. Okay. Now, on this picture, I'm going to sketch two planes. Okay, first of all, I'm going to sketch, or at least a part of the plane. The part I'm going to need. So this is the plane. I'll say part of the plane x equals x naught. So there's a vertical plane. We are not contented with all that. Make this thing look like a variable. Leave the grid out of it. Although the grid doesn't have any bearing on the coordinate system. Does that make sense? Can you see where that plane is? Like it goes through the x equals x naught z equals 0 line at this point. And at this point that I unfortunately can't mark because I labeled x equals x naught there. Didn't have the foresight to put this thing someplace where I could label it. But you understand, that's a plane. And it's not. Okay, every point where x equals x naught is on this plane, and every point on this plane has x equals x naught. We understand? Okay. Now, we're going to cut the graph of the function. Now, the function could be quadrant function, could be any function. Okay, could have peaks and valleys and swirls and everything else, as long as it's a function. So it's going to go through this point. And let's just say that at this point, it goes through here. This. We'll say this is the line f of x naught y. And just to be official, we'll say because x equals x naught. Okay. So whatever that surface is doing, we cut it with the plane perpendicular to the x-axis, and we get a curve. Okay. Just as you can imagine that I cut this block out of a beautiful sculpture. Okay. By slicing it here, slicing it here, slicing it here, slicing it here, slicing it at the x-axis, xy plane, and slicing it here in this other plane. Okay. What we're really after is the equation of the plane at the top of this thing. And actually, I didn't slice it this way. This was the top of the sculpture. Okay. It looked fairly flat here, but there may be some curvature that we can't see when we look at this. Okay. Now, the curve I just drew is the curve that I get if I slice the sculpture here. Okay, so you got this curve that's doing this and then it does this. Okay, well, there's that curve. It doesn't look exactly like it should. Can't make that thing go down. Well, there it is. Okay, so curve comes up and it goes downhill a little bit. Right there at that. This point. Makes sense? Now, I can sketch the plane perpendicular to this one. And I'm gonna extend this line out. Yep. I'm gonna come up over this line and then down. Same thing, except I can't go on top of it. Then I draw right here, parallel to the y-axis. Supposed to be parallel, but I think I quite made it, but and again, parallel to the y-axis and meet up with this line out there someplace. And now I've got a plane. Lose my vertical. It looks kind of like this. Okay, and this plane is perpendicular to this one. You kind of visualize that? Okay. So that if I cut, say, if I slice the function this way, maybe the graph does this here. Now this is in this direction, okay, parallel to the x-axis or the xz plane. So these two curves are crossing, they're perpendicular to one another. Okay. Well, then this plane z equals f of x naught y, etc. And this plane, and I call this a line, this is a curve. Call this curve. In this plane, I sketch a tangent. And in this plane, I sketch a tangent line. Now I could improve that sketch. I probably should have kept this thing concave down further so you could clearly see the tangent line, but you understand that there would then be a vector along the tangent line. Okay. Make sense? Let's just say that I had a little sense and drawn my curves like this. Then we could see a tangent line here. It doesn't intersect with the graph itself, right? In a tangent line here. This one in the plane perpendicular to the perpendicular to the x-axis, parallel to the YZ plane. This one perpendicular to the y-axis, parallel to the XZ plane. So I kind of screwed up that picture, but tangent vector. Well, this tangent vector could be J because it's in the J direction, right? But it's also got a Z component. So I'm going to use one for the component of the, well, for the J component. Plus the y derivative of f times k. Now, are you familiar with the f sub y notation for the partial with respect to y? I'm pretty sure that was introduced in the section. I didn't actually look to be sure, but it's typically introduced by this point. And this one is I plus fx a. has good pictures of this. And the reason for this is simply that Fy is the slope of this thing. It's the slope of this curve or this curve at this point, if you confine it to the x equals x naught plane. Okay? And y is your variable. Treat y as your independent variable, z as your dependent variable. Then the y derivative gives you the slope of this thing. Well, the slope of this thing is rise divided by run. The rise is your k component, the run is your j component. So rise divided by run is Fy divided by 1, which is Fy. Does that make sense? I'm going to write it out. It's the run. Rise of Fy, run of j. Similarly, here you got a rise of Fx and a run of, not a run of j, a run of 1. Run is 1 because you have going 1 unit in the I direction. The rise is Fx because you're going Fx units in the k direction, right? Where Fy and Fx are evaluated at x naught, y naught. In other words, this is the y slope at the point x naught, y naught, f of x naught, y naught. This point is x naught, y naught, because that's your x and y coordinate, and f of x naught, y naught, which is this. The tangent plane is through x naught, y naught. Normal to the cross product of these two vectors. Because this vector is in the plane, at least it's tangent to the plane at this point, and this vector is tangent to the plane. These are two vectors tangent to the plane. I say tangent vectors, I mean tangent to the plane. You can read about it. But these are normal to I plus fxk crossed with j plus fy. I know the cross product of these two vectors is normal to the plane. Now, I cross j is k. I cross fyk. Well, I cross k is negative j, so we have negative fy k. And k cross j. Uh-oh. I cross k is negative j. K cross j is negative. I mean, I knew it had to be negative, but I wanted to double check it. So if you're thinking a little more clear than I was, actually immediately obvious. There's a normal vector. There's a point. Okay. So that the equation of the plane point X, Y, Z, it's in the plane. We have the normal vector. Normal to the plane. We have this vector in the plane. So for him to write it, we want that to be somewhat clear. There's this vector. And I'm not going to assume X, Y, Z is in the plane. I'm going to write down if and only if this vector is perpendicular to this. Now, this vector is perpendicular to this one means the dot product of this vector with this vector is zero. Now, I wrote this vector in terms of a ordered triple with an arrow over it, okay? But I wrote it in terms of I, J, and K components here, except I didn't put a K over K over it. K's in there whether you can read it or not. But what's the dot product? It's this. Which is of the form Hey, don't memorize this as an equation. You simply see how to derive it, and then you just use the numbers. Okay? So for an example, say you got this relatively simple function, f of x, y, at the point 2, 3. And what's f of 2, 3? It's going to be 4 plus 27. No, so it'll be 4 times 3, which is 12, and 27 times 2, which is 54. I think it's 66. Okay. So 2 squared is 4 times 3 is 12. 3 cubed is 27 times 2 is 54. 54 and 12 is 56. So that should be correct. Okay. So let's see. Fx is 2x y plus y cubed. Fy is x squared plus 3x y squared. Fx at 2, 3 equals, careful, 2 times 2 is 4 times 3 is 12 plus 3 cubed is 39. Fy at 2, 3. And let's not trust my arithmetic too much. 2 squared is 4. X, y squared is 18 times 3 is 54. 4 is 58. So let's pretend those are right. You can correct it if you need to. And make everything come out nicely. So I want to show you how the tangent plane approximates plane at a point near 2, 3. So the normal, if I've done this right, would be the cross product of the two vectors that we obtained here, I plus fxk and j plus fyk, and that cross product is going to be, I think I did it wrong. Where did I do it? There. K cross j gives me I. Okay, so I thought about it there too. Something didn't seem right about that, but right, I think. If it's not, you'll get it wrong. Okay. This equals what? And I wrote down my I think my attention, right? Seems for me to get things confused. Okay, I cross K again is negative J, but I've got negative 39 here. So I think I'm going to get 39 J and 58 I plus K. Now, does that make sense? Okay. fx is 39, fy is 58. So the vectors are like this and like this. They'd be back like this. Bigger component in this direction and this direction, and there it is. Okay, I think that's right. But we got somebody's hand up, which means it probably isn't. So let's check it out. All right, now I got the habit, I just have plain old K here and plain old I here, and plain old J here. So I put plain old K here. But yeah, that's right. No, it's right. I cross J is K. There's no fx or fy on anything that's equal to K. The fx is on the K component crossed with the J component. K cross J is negative I. So the fx goes with a negative I. Okay. Fy with the negative J similarly. Okay, so thanks for questioning that. I think it's right. If I do this, what's K cross K? K cross K is 0. Okay. So I get negative 39I cross K. I cross K is negative J. I got a negative on the 39, so I get 39J, etc. And it's in this direction. It'll be into the first octant if I just visualize these vectors. So I'm pretty sure that's right. And if it's not, just do it right when you do it. Okay. It's going to be a pretty flat vector because both of these tangent vectors are pretty steep. So if I take a tangent vector that's steep this way and slightly in this direction, with a tangent vector that's steep this way and slightly in this direction, in this direction, they give me a cross product that's pretty flat, but it's out into the first quadrant or the first octave. So the normal is this. So the equation of the line is this has to be perpendicular to this. Because if x is in the plane, then this vector is in the plane. If x, y, z is in the plane, since the point 2, 3, 66 is in the plane, you have the vector from the point in the plane 2, 3, 66 to the point x, y, z, which we assume is in the plane. And that vector, which is in the plane, has to be perpendicular to the normal vector. So the dot product is 0 because this is supposed to be normal to any vector in the plane. I don't have room to write that out, but it was stated over here. Dot product is 0. Thus, minus 2. Sorry. 58 times x minus 2 plus 39 times y minus 3 plus z minus 66 has to equal 0. Well, that tells me you've got 58x plus 39y plus z. Then it's minus 116 for this, and minus 107, which is minus 223 for this. And that's 289, I think, minus 289 equals 0. And that's the equation of my plane. Now, if I want to do it z equals, well, then it's going to be z equals negative 58x minus 39y plus 289. Okay. So I could do z equals very easily. I can put this plane in any form I want to manipulate it. Okay. Now let's test whether this makes good sense. If this plane is tangent to this thing, it's pretty obvious if you think about it that this function is nice and smooth, has nice smooth partial derivatives in any direction, okay? I mean, these are smooth functions. These are simple power functions, integer power functions, nothing weird. So it's probably pretty smooth. And you can worry about that when you worry about limits and so forth. Um, so plane z equals negative 58x minus 39y plus 289. If my arithmetic is correct, that's questionable. Well, approximate. Z equals f of x, y equal x squared y plus x y cubed. For x, y close to 2, 3. Okay. Consider x, y equal 2.1, 2.9. Then z equals negative 58 times 2.1 minus 39 times 2.9 plus 289. Should be close to z equals 2.9 squared times 3.1 plus 2.9 times 3.1 cubed. Okay. Now, if you've got a calculator handy, go ahead and do this because I don't want to attempt to approximate this. I can do it, but there'd be at least 50-50 chance I'd have some bonehead mistake. Like 3.1 cubed is 3 plus 0.1 cubed, okay? Which is 3 plus 3 times 1 squared and 3 times 3 squared times 0.1 and 0.1 times negative 0.1, and I forgot the negative 0.1. It's you know, there's a lot to remember, and I don't trust my working memory to do that approximation. So use your calculator there and do that kind of quickly. Don't spend too much time writing, and I'll approximate this. Actually, so again, That's like 194. That's like 1.9. So that should equal 89 and 4.1. And my value is 66, so something's probably off. I didn't multiply my y by 3, I multiplied it by 2. So that should have been 107. And now if I subtract 39, this, I get 58. Maybe something like that. Now, I don't want to spend a lot of time. What'd you get? Let's pause and tell me what you got. Okay, so people with calculators got 64.01. Now notice that that's pretty doggone close to 66, right? And for a lot of reasons that you could reason out by the relative slopes of these in the X and Y directions, that probably makes a good bit of sense. Now, my calculation here. Oh, wait a minute, did you do this one? Did you use 2.1? Don't say it, just tell me yes or no. Use 2.1, not 2.9. X should have been close to using a 0.23, I think, right? X should have been close to 2, Y should have been close to 3. Oh, wait, didn't I use 2.1 and 2.9? Oh, I got my numbers all screwed up. Okay, if is that what you used? Okay, well, using the right numbers here, which should have been 2.1 and 2.9. Get about this. Now, if I evaluate this correctly, and I think I did 2.1 right. I screwed up 2.9, but did it up here. I used 2.1, 2.9. It didn't screw it up because 3 times 39 is 107. And minus 0.1 times 39 is 3.9. I might have screwed up the 289 when I did the calculation there. This is what you get from the function. What I got up here is like 58.1, just that far from it. But just moving a tenth in each direction, even though the slopes are big, second derivative is not that big. But it's kind of big over here. So I'm thinking about things that we don't understand anyway at this point, but we'll talk more about it later. So for various reasons, I still think that's a little too far off, but if you do this calculation, very simple calculation, this one. Go ahead and do it. Just take a second to punch that in, see what you get. And then I'll move on. Let me take a quick look at where we're headed. Now, something to think about here. Just think about it. Don't try to actually do it. Just, you know, when I've talked about the second partial derivatives. Okay, if the second partial derivatives are all 0, that means this thing is a perfect plane. If all the first, if there are no second derivatives, there's nothing to make either of these functions curve. Okay, if the second derivatives are all 0, then this thing is a plane to start with. You just got to have a constant times x plus constant times y plus any constant number. Okay, if you have anything else, your second partial derivative is not going to be 0, And this number is not expected to match this number. This number has been correct. It should have been 299. You know, I told you my working memory is a little bit funny, and I'm not writing anything down. So I got 289. It's 290. Or is this what should have been 290? Okay, this should have been 299. Well, then, of course, that one would have been 299. So there's your correct equation, plane. And if you plug 2, 3, and 66 in here, that's what I did. 107 and 116 is 223, 23, I still get 289, but I believe your calculator, and this is better than this one, so I like it better. Okay, now what I'm saying is, it's the second partial derivatives that make this different from this. Because without second partial derivatives, this is a plane, and this is going to be the same plane. It has to be, okay? Now, because of the second partial derivative, so you're going to get some variation here. Now, there's a definition that says a function is differentiable. Basically, if as you approach the point 2, 3, closer and closer from any direction, you approach this value as a limit. Okay. If that's so within any small region and containing the point inside of it, then the function's differentiable. That's what the definition of differentiable is. So you might want to read that and think about that a little bit. It's an important concept. As fast as we're moving, we're not going to have time to delve into it deeply. And I don't think I've assigned any problems that actually cause you to have to do that in the theoretical way, although I'd love to have you do that. We just need more time. And we're kind of sacrificing that so we can be sure to get to the integral theorems, which are likely to do you more good than the deeper theory. Okay, but I hate to leave anything out at all, and that's one of the things that I really hate to leave out. Okay, hurrying too fast and making mistakes. How do we get K? It's not from these K's, is it? They give you 0. So this should have been 39 times 58 times K. Okay. And that comes out, what'd you say, 2262? That seems about right. It's a little less. 40 times 60, which is 2400. Okay. Then that's going to change coefficient of this term. It'll be 2262 times this, which will change this number accordingly. And that's going to be something like 2/3 of that would be a little 700, about 70,000. 70K, I can't write 70K for 70,000. I'm just going to write 3 zeros there. So that was screwed up. That number is different. And this number in front of Z is 2262. That's really small, but it says 2262Z. That's going to change a bunch of stuff, but it's not going to change principle. 149,000, wait a minute. You're right. How did I get that? 2/3 of that would be 2/3 of, say that, that's going to be like 200,000, and 2/3 of that, yeah, would be 140,000. Okay. Recorder. Okay, basically, I really messed up, sir. I apologize. Read your book. The whole picture is the picture I gave you. And if you replace this with the right Z and solve this for Z, meaning you're gonna have to divide by 2262, it's gonna change a bunch of stuff. These two are still gonna come out pretty close. They'll probably come out in proportion. This is off by about 6%. It's probably gonna be pretty close. So this is based on the wrong equation, based on incorrect equations. It's the right equations done incorrectly. So we have that. Now, my point is, if you do this correctly and remember that the I component times the J component gives you the K component, so these coefficients multiply to give you the coefficient of K in the normal vector. So when you do the dot product, that changes everything on this Z. Okay. And then it changes everything over here. Still do the same stuff. You just have to change most of the numbers. Okay. This is based on the equation I originally had, where this was x squared y plus xy squared, and they're 2, 3. Okay. Plug those things in, and you're still going to get this, I think. Okay. And then because of the way things are going to work out here, this works out. This is based on any error of this function. Okay. What this function should be, I think, is Z equals 58x plus 39y plus 149,000 and change that you can write out, all divided by 2262. Okay. When you divide this by 2262, please, well, that's going to change the numbers that you put in here. Not going to change the numbers you put in here. And it should work out where this number and this number might be a little different. This number is still going to be what it is. Okay. And this number is still going to be kind of close to this one. Since this came out as close as it did, and I don't want to go in and analyze where this factor and everything changes quantities. You know, 2,200 into 140,000 is around 70. So this is going to kind of dominate it. It's going to be somewhere in the neighborhood of 70, and then these things are going to have their effect to mitigate that 70 and probably get it closer to 64.01. Okay, so that's a tangent plane, and it approximates the value of the function. Those are the two things you really need to know. Okay. Okay, now the change in f of xy change in X is 0.1, change in Y is negative 0.1. Okay? Fx at 2,3 is 58. Fy at 2,3 is 39. Fx delta x plus Fy delta y is 58 times 0.1 plus 39 times negative 0.1. Well, that's just like 58 minus 39 times 0.1. 58 minus 39 is 19. That should be negative 1.9. Okay. So f of xy should change by about negative 1.9. No, sorry, it should about 1.9. Looking at the negative sign there, it should change by about 1.9, which means that this approximation here, if done with the correct function, could be about 65.9. Okay. So work that out with the correct function and see if it isn't about that. Because why? Because x is changing by 0.1. So the change in 58x will be 5.8 if you like. Y is changing by negative 0.1. So the change in y will be negative 3.9. So the net change will be about negative 1.9. And none of this changes when x and y change, because none of this depends on x and y. So this will, I think, will probably come out about 65.9. Again, if you use the right numbers, and it's worth working that out or working out something equivalent in the homework. Is that what you got? So should have been 65.9 or 65.91. Okay. Well, that's all we got done today, but get the tangent plane down real well and read the section on the, I think it's the partial derivatives. I can tell in just a minute. I mean, chain rule. Okay, so at least review the chain rule real well so that you're good with that. And we'll move on from there.